One day, Ms. Dobashi and Ms. Schultes have a disagreement. Ms. Dobashi claims that 20% of CCA students have taken a stats course, while Ms. Schultes believes that less than 20% of all CCA students have taken a stats course. How can Ms. Schultes use a statistically appropriate method to address this disagreement? That's the premise of Chapter 9, Significance Tests. So with every significance test, we first need to state our null hypothesis and our alternative hypothesis. We want to find evidence against the claim that the proportion is 0.2. And we want to find evidence for the claim that p is less than 0.2. We always need to define what p is. It's the true proportion of CCA students that have taken a stats course for this problem. A common student mistake is to use p hat instead of p, but remember, we're trying to talk about a population. Lastly, for the state part, remember to include a significance level. If it's not already specified by the problem, this is 0.05. So one day, Ms. Schultes decides to take a random sample of 65 students and finds that 11 have taken a statistics course. There are three conditions for inference for a one-sample z-test for proportions. We need to prove that there's either random assignment and random sampling. The problem states that there's random sampling, so that condition is satisfied. The next condition is the large counts condition. We need to prove that n p naught is greater than or equal to 10. So we plug in our sample size and our our null hypothesis proportion. A common mistake is actually to use the sample proportion. And we need to prove that it's greater than or equal to 10, which is true. There's also the 10% or the independence condition, but this is not tested on the AP tests, so it might be a good idea to actually not include it. But what it says is when we're sampling without replacement, the sample size should be less than or equal to 1/10 of the population size. And then state what test we're doing. The conditions have been satisfied, so we can use a one-sample z-test for a proportion. The next proportion is the work. The z-statistic is essentially a z-score, if you may remember it from normal distributions. So what we plug in is a sample proportion, and we plug in our null hypothesis proportions along with the sample size, and we can calculate a z-statistic of negative 0.62. Our p-value is the probability of obtaining a result as extreme as the one we got in our sample. Remember, for two-tailed hypotheses, for example, if we did a null hypothesis where p is not equal to 0.2, we'd have to multiply this by 2 to account for the other side of the normal distribution.
Now, before we move on to the conclude step, let's take a look at the other type of test, the one-sample t-test. The one-sample t-test is meant to estimate a population mean, and as you can see, the hypothesis stem is mainly the same, except for the fact that you use mu for the population proportion. In addition, and for the conditions, instead of having n times the null proportion be greater than or equal to 10, you want n itself to be greater than or equal to 30. This is meant to ensure that the data can be assumed to be normal. If our sample size is less than 30, do not fear, we can take a histogram of the sample proportions or a normal probability plot to ensure that the data is approximately normal with no outliers or strong skew.
And this t-statistic is a little bit different. As you can see, here's the formula where x bar is the sample mean, null hypothesis mean, standard deviation of the sample, and square root of the sample size. The t-distribution actually changes based off your degrees of freedom, which is n minus 1. If you're using a chart, sometimes they won't have the value for your specific degrees of freedom. For example, for sample size of 54, we have a degrees of freedom of 53. We should use the lower one, 50, instead of the larger one, 55, because it's more conservative. And the p-value is the same. But remember on your calculator to plug in the degrees of freedom, because that actually matters for the t-distributions. And that essentially gives us our p-value. What's the probability of obtaining a result as extreme as the one we got in our sample, assuming the null hypothesis is true? If the p-value is less than the significance threshold, we reject the null hypothesis, and we have convincing evidence that the alternative hypothesis is true. If the p-value is not less than the significance threshold, we fail to reject the null hypothesis. We do not have convincing evidence that the alternative hypothesis is true. As you might notice, we never accept the null hypothesis. So let's go back to the previous problem. Include an explicit comparison between the p-value and the significance threshold. Because the p-value is not less than the significance threshold, we fail to reject the null hypothesis. We do not have convincing evidence that the true proportion of CCA students who have taken a stats course is less than 0.2. And congratulations, you've just completed number 4 from the 2005 AP Statistics FRQ.
So how would we use our calculator to solve statistical tests? It's pretty intuitive. First, on your TI-84, you would click the Stat button, press the right arrow 2 times to get to the Test section. Now, you can see that we can either use the t-test or the 1 proportion z-test. It is very important that you scroll down to 5 for a 1 proportion z-test, because the normal z-test assumes that you know the population standard deviation.
After that, the interface is actually really clear. For the 1 proportion z-test, you can see that we just plug in all these values and click calculate to obtain your p-value. For t-tests, it's actually basically the same, where you can just plug in the stuff, except you can choose from data or stats. If you do data, you provide the data in the form of a list, which you will reference. Whereas for stats, you should already have the population, or the sample mean and the sample standard deviation.